Good afternoon, everyone. I'm Amit Kumar Pal, currently third year undergraduate from Indian Institute of Technology, Kharagpur. So, in the last term, we had completed almost half of the part of this exercise. So, we'll be covering the rest part of the exercise in today's session. So, we'll be solving more questions and more concepts. Basically, in the previous session, most of the questions were theoretical, I think, because most of the questions involved only theory and putting your understanding about the gravitation into the answer. Okay, but for the coming questions, we'll be requiring more numericals and understanding of a vector field and potential, etc. So yeah, we'll be working on that side. So yeah, let's start. I think we had completed almost 9 questions, I think. So we'll be starting with question number 7.10. Okay, so let's start. Let me decrease this thickness. So uh, if I read about the question number 10, so it says that in the following two exercise, choose the correct statement answer from among the given ones. The gravitational intensity at the center of the hemispherical shell of uniform mass density has a direction indicated by the arrow A, B, C, and 0. So basically, you have to tell about the direction of the gravitational field at the given points. Okay, so yeah. So if we describe something about the hemispherical cell, so you know that if this is a hemispherical cell, then gravitational field at every point inside the sphere is 0. Okay, by 0 we means when the sphere is complete, means it is uniform sphere without any irregularities. So electric field at any point inside the sphere is sphere is 0 basically. Okay, and if we suppose if we cut down this sphere into two parts, so basically this is hollow sphere, so we are cutting down this sphere into two parts. Okay, so we have to tell about the direction of the electric field gravitational. Basically, the concept for electric field and gravitational field runs parallelly. Okay, whatever concepts hold for gravitational field also holds for electric field as well. Okay, so हम कह सकते हैं कि gravitational field एक electric field का ही एक analogy है, but only difference is being कि वहाँ पे हम charges से deal करते हैं, but यहाँ पे हम mass से deal कर रहे हैं. Okay. So, okay, let's start. Let's figure out this question. Okay. So, if we understand the question once again, so it says that it is saying that the gravitational intensity at the center of the hemispherical shell of uniform mass density has a direction indicated by the arrow. So, let's say if we remove the above half part, okay, so it is basically asking what would be the direction of electric field now. Let's wait for a few seconds. It is taking some time. Actually, sorry for some inconvenience. It is taking some syncing time, so I'll be waiting for a few seconds to get it fixed. Okay, so finally it is fixed. So we'll be continuing our solution part again. Okay. Yeah. So we have to find about the direction of gravitational field at point C. Okay, C is this point. So if we consider only half part of this hemisphere, so this is half part. Okay, so you know that net field is 0 because of this whole sphere. Okay, so uh, to consider the uniformity, we can say that the net field is 0 only when this part and this part apply the equal gravitational field in opposite direction. Okay, since this is a massive particle, so gravitational field will be in this direction, and to make this field equals to 0, this part will be creating the gravitational field in this below direction. Okay, only then the gravitational field is equal to 0 at this point. Okay, so we can say that the direction of the direction of gravitational field is in the direction of below. Okay, at point C, it is straight downward to the point C. So this is about this part, and if we move to the next part, that is 7.11. Okay, so this says that for the above problem, the direction of gravitational intensity at an arbitrary point P is indicated by the arrow. So you have to find the direction at any arbitrary point C P. Okay, and this is your hemisphere, hollow hemisphere, and this is some point P. Okay, so what can you conclude about this point P? Okay, there are four directions mentioned. One is this direction, and other is this direction, and one is completely below this direction, and other is this direction. Okay, so since this is a mass particle, so and gravitational field is inattractive in nature, so we can say that the field cannot be in this direction or this direction, because these are basically some repulsive direction. Okay, so this cannot be in this direction, and we are left with only two choices, this and this. Okay, and now if we consider about this complete mass, we know that this mass is completely distributed from this region to this region. Okay, so this cannot be completely in this direction, because some mass is here as well. ओके, यहाँ पे भी थोड़ा मास है, तो इसकी वजह से कुछ इलेक्ट्रिक फील्ड, ग्रेविटेशनल फील्ड के कंपोनेंट इस साइड आएंगे. ओके, इस साइड भी आएंगे तो उसकी एंड कुछ मास इस साइड है, तो उसकी वजह से कुछ कंपोनेंट इस साइड आएंगे. ओके, सो क्या होगा कि यहाँ पे कुछ मास क्लोजर टू दिस पॉइंट एंड यहाँ पे कुछ mass farther to this point. Okay, so what happened, we can approximate somewhat direction would be something like this, because these vector will get cancelled and only the below vector will be remaining. Okay, so we can say that the net direction of gravitational intensity at this point will be in straight downward direction as well, or we can say that it would be in direction of E. Okay, so this is about this question, and basically you have to put your reasoning here and consider what can be the direction of intensity at those point. Okay, and now if you come to the next question, that is 7.12. So if you read about the question number 7.12, it says that a rocket is fired from the earth towards the sun. At what distance from the earth's center is the gravitational force on the rocket is zero. Okay, uh, so you have to find some equilibrium point. Okay, and you can consider about this equilibrium point in this way, like let's say this is our question, let's say this is our earth, and this is some this is sun. Okay, sun is basically much bigger size than earth. Okay, and let's say this is a distance between their centers. Okay, since the gravitational force is central force, so basically most of the time we are interested in the distance from the center, so because we consider that for a long distance this planet acts as a some point object. Okay, and for considering them as a point object, we consider them as if their complete mass is located at their center. Okay, so this is about the concept of central distance, and you have to find basically some rocket is fired from this to this. Okay, so you have to find at some distance the net force on the rocket is zero. Okay, so you have to find that point. Okay, now if we think something apart from the question, so you know that this mass of the earth is much smaller than the mass of the sun. Okay, so you can say that the gravitational field will be zero somewhere closer to the earth and farther to the sun, because the mass of the sun is much larger than the earth. To make the forces equal to forces balanced, basically this distance should be more. Okay, because the gravitational force is inversely proportional to the distance. Okay, only then the counter effect of mass will be balanced by the distance. Okay, so let's say this is some distance x, and this is some distance r minus x. Okay, where r is the total distance. Okay, so if we write the equilibrium equation, that is yeah. Okay, so basically you have to write field due to a field gravitational field due to the earth is equal to gravitational field due to the sun at that point, at some point a. Okay, so we can say that E of equals to E of sun. Okay, so you have to solve this equation. Okay, so if we put the values, so G of any of x square equals to G of mass of sun upon r minus x whole square. Okay, so if you take this as here, r minus x upon x whole square equals to mass of sun upon mass of earth. Okay, now you know that r is given equals to 1.5 into 10 to the power 11 meter, that is orbital distance, and mass of the sun and earth is also given. So if you put the values, then it comes to be whole square equals to square root to the both the sides. So we can solve the linear equation between x. Okay, so this comes out to be so if we solve the linear equation between x and r, so it gives r minus x by x equals to this comes around 527. Okay, so we can say that x is nearly equal to r by 578. Okay, so if we put the value, so x equals to 1.5 into 10 to the power 11 by 578. Okay, so this comes x equal to 2.59 into 10 to the power 8 meter. Okay, so this is our final distance at which the net intensity will be equal to 0, and the net force experienced by the rocket is equal to 0 between the earth and sun. Okay, so now if we move to our next question, that is 7.13. So in the question number 7.13, you are said that how will you weigh the sun? That is to estimate its mass. Okay, so it is about weighing the sun, and you of course don't have to do it directly, but you have to find some indirect way to do this. Okay, so uh, we'll try to find some ways how we can do this. Okay, so if you are familiar with the Kepler law of motion, so it says that time period of revolution of the planet is directly proportional to the square of time period is proportional to the cube of the semi-major axis. Okay, so if we consider about the Earth and Sun system, okay, let's expand this formula completely at first. Okay, so you know that the time period t square is given by g into m by 4 pi cube. 4 pi, this is square basically. This one is we derived in the last lecture. So from here we can find the mass as m equals to t square 4 pi square r cube. Basically the formula is reverse of this formula. There is some mistake in this formula. So t square is directly proportional to the r cube. Okay, so we can say that t square equals to 4 pi square r cube by gm. Yeah, this is correct. Okay, so from here we can say that mass of the sun is equal to 4 pi square r cube by g t square. Okay, so if we put all the values, because we know all the unknown parameter, and they are already given in the question, or we already know the value of those parameter. Okay, so we can find mass of the sun equals to 4 into let me open another text editor to solve the question, because this is creating a lot of problems here. Yeah, so we'll be solving question here now, because whiteboard was lagging a lot. Okay, so like in the previous part that we have derived, basically m equals to 4 pi square r cube by t square. Okay, so if you put the values, then m comes equals to 4 into 3.14 whole square into then r cube. So r is given 1.5 into 10 to the power 11. Okay, so this is, and g equals to 6.6 into t square. So t and the important thing to understand here is that what is t. Okay, t is basically time period of the revolution of the earth around the sun. Okay, because we are considering earth and sun system. Okay, so t equals to 1 year. Okay, so this is equals to 365.25 into 24 into 60 into 60 second. Okay, so this is the value of t. Okay, this is important thing to understand, because if we are considering the system of two planets, then time period is basically time period of the revolution of the planet around that central body. Okay, so if we put that value of t square here, and now we'll be solving this complete expression to find the mass of the sun. Okay, so if we simplify this expression, then you will notice that the result comes around to be equals to 2.1 something into 10 to the power 30 kg. Okay, so this is the mass that comes out to be. Okay, so this is all about this part, and uh, now if we move to the next question, that is 7.14. Okay, so the 7.14 says that the Saturn year is to 29.5 times the Earth year. Okay, how far the Saturn from the Sun if the Earth is 1.50 into 10 to the power 8 kilometer away from the Sun? Okay, this is nothing special, but this is simple implementation of Kepler's law that says that the time period of the revolution of the planet is proportional to the that is square of the time period is proportional to the cube of distance from the center body. Okay, so this says that t square is proportional to the a cube. Okay, so let's say this is our sun. Okay, and this is one of the radius of the planet, and this is another planet. Okay, so we can consider this is as a Saturn and this as a Earth. Okay, so you have to basically tell about the uh, this distance. Okay, this distance of the Saturn from the Sun. Okay, and you already know this is one astronomical unit. Okay, one astronomical unit is the standard unit between the Earth and the Sun. Okay, so if we consider the same thing, then TE square upon TS square equals to AE square by AS square. Okay, where AE is the orbital radius of the Earth and AS is the orbital radius of the Sun. Okay, so you have to find the AS. So this is cube actually, because it is proportional to the cube of the distance. Okay, so AS is basically equal to AE of T, this is TS by T to the power 2 by 3. Okay, so we just have to put the values here, nothing else. So if you put here the values, then it comes as equals to basically R equals to A equals to 1.5 into 10 to the power 8, as we have seen this distance in the above question as well. So this is, and Ts by Te is basically the ratio of the time period of the revolution. Okay, so as the question says that the Saturn year is 29.5 times of the Earth year. Okay, so that means the Saturn takes 29.5 times that the Earth takes to revolve around the Sun. Okay, so we put these value, then AS comes out to be equals to around 14.3 into 10 to the power 8 meter. Okay, so this is the required distance. Okay, yeah, so this is about this question, and we'll move to the next question now, and we'll see what is coming to the next. Okay, so question number 7.15 says that a body weighs 63 Newton on the surface of the earth. Okay, What is the gravitational force on it due to the Earth at a height equal to half of the radius of the Earth? Okay, so you know that weight equals to mass into acceleration due to the gravity. Okay, so this is the weight. Okay, and as we have derived in the last lecture that as we move above to the surface of the Earth, the acceleration due to the gravity decreases as well. Okay, and we had seen the formula g dash equals to g times 1 minus 2h by r. Okay, but the important thing to understand here is that is this formula is valid in this case. Okay, so I'll give you a I'll give you a few seconds to understand if we can apply this formula directly here as well or not. Okay, so if we consider about the derivation of the above formula, we had considered that 1 plus x to the power minus n equals to 1 minus nx. This was the approximation that we had considered. Okay, but this approximation cannot be applied here because the x is not small, because as the question says that we are going to the height equal to the half of the radius. Okay, at equals to r by 2. So, or we can say that we are going to the height equals to r plus r by 2 from the center of the earth. So, of course, we cannot apply this formula directly here. Okay, so we'll need the general formula for the calculation of the acceleration due to the gravity. Okay, so you know that acceleration due to the gravity is equal to gm by r square. Okay, where r is the distance from the center of the earth. Okay, and at a height equals to 3r by 2, this is equal to gm by 9r square into 4. Okay, so this is the acceleration due to the gravity. Okay, so this is basically equal to 4 by 9 times of g. Okay, where g is the gravity on the center of on the surface of the earth. Okay, so we can consider we can find now weight equals to m of g dash. Okay, m into 4 by 9 times of g. Okay, so new weight equals to 4 by 9 times of initial weight. Okay, so this is equal to 4 by 9 into 63. So this is equal to, so this is our final answer about this part. Okay, and if we now move to the our next question, that is 7.17. So it says that a rocket is fired vertically with a speed of 5 km per second from the Earth's surface. How far from the Earth's surface does the rocket go before returning to the Earth? So mass of the Earth is 6 into 10 to the power 24 kg, and mean radius is given equals to 6.4 into 10 to the power 6 meter. Okay. So you know that the escape velocity from the Earth's surface is equal to around 11.2 kilometer per second. Okay, so this is the escape speed from the Earth's surface. So from this value, we can approximately say that any speed below this speed will always lead the object to fall back to the surface of the earth. Okay, अगर किसी भी ऑब्जेक्ट की स्पीड इससे कम होगी तो उसे वापस जरूरी आना है, क्योंकि सफिशिएंट स्पीड ही नहीं होगी अर्थ की ग्रेविटेशनल फील्ड को ब्रेक करने के लिए. ओके, so we can say that this rocket is going to fall down the surface of the earth. Okay, and basically we have to find the distance from the earth's surface, or we can say that we have to find the distance uh, above the earth's surface that the rocket will reach. Okay, so let's say this is our earth, and this is some height h. Okay, so at this point the velocity will be equals to 0, because only then the rocket will stop moving forward and it will fall back to the surface of the earth. Okay, so you just have to find this distance. Okay, so this is something, but you have to just do the simple conservation of energy, because there is no loss of energy. Okay, there would be some loss of energy due to the atmospheric air present or some other factor, but we don't have to consider in this case, because as such nothing is mentioned in this question. Okay, so if we write kinetic and potential energy at this point A and B point, then we can say that minus g m e into m by re plus half mv square equals to minus का g m e into m by re plus h. So this is simple energy equation plus zero because there is no kinetic energy at the maximum height. Okay, so we can cancel small m from all the sides, so we finally get the expression as it is. So we can simplify this as twice of g me upon h upon re into re plus h. Okay, this is our final expression, and if we put the values here, and if we take a re common from this bracket, so this become equals to v square equals to twice of g me by re square into h upon 1 plus h by re. Okay, and this is nothing but this is acceleration due to the gravity, so this is equals to twice of g h upon 1 plus h into re, h by re. Okay, so if we simplify this expression, we come to the h equals to re into v square by twice of g re minus v square. So this is our final expression for the height. Okay, so if we put the values, because all the values are given in the question, so we can simply put into v square equals to v is velocity is 5 kilometer per hour. Okay, so we can convert it to the meter per second. Okay, or sorry, the velocity is given equal to 5 kilometer per second. Already it is given in a second, so we have to just convert it into a meter. Okay, so इसे कर लेते हैं मीटर में कन्वर्ट, एंड जी की वैल्यू भी हमें पता है 9.8, एंड रेडियस भी पता है हमें माइनस वी की अगेन वी की वैल्यू. Okay, so this is our final expression, and we can solve this expression to find the value of h. Okay, so you can solve this value by simply, this is simple calculation. So if we solve the above expression, then height basically comes equals to around 1.6 into 10 to the power 6 meter. Okay, so this is the tentative height that we get finally, and this is above the surface of earth, and if we have to find from the center of the earth, then we can add equal radius as well equals to, so net height equals to h plus re. Okay, so re equals to 6.4 into 10 to the power 6, and h equals to 1.6 into 10 to the power 6, so net result is equal to 8 into 10 to the power 6 meter. Okay, so this is about this question.